All right. Good evening, everyone. Let's get started. I know you're all excited to learn about some calculus, or review some calculus on Saturday night with just under 36 hours to go until our final exam. So I wanted to start out by working through the indefinite integral dominoes activity, which I did with my class yesterday. You might have seen it earlier in the week. I think officially it's on the calendar for this past Wednesday, but whenever you did it, there are a lot of integrals here. You should expect to see some integrals on the exam, definite, indefinite. And the thing about the dominoes activity is that there's a little bit of a shortcut, which is that you can look at all of the integrands and differentiate that. Or sorry, you can look at all of the bottom halves of the dominoes and differentiate them and look for those integrands and integrals. So I know some of my students were going about it that way, and that's a really intelligent way to go about this activity. But I wanted to go through all of these integrals and make sure that you all are comfortable starting out with the integral and actually finding an antiderivative without necessarily having the bottom halves of the dominoes to look through. So that's where we're going to begin. And as always, send me a message in the chat if you have a question. Thank you, Roses of May. Or feel free to shoot me an email too if you don't have a Twitch account or you don't want to send a message in the chat here. I am keeping an eye on my email. I'm happy to answer any and all questions. After we go through this activity, my plan was to work through the practice exam from spring 2025, and then we'll see where the night takes us. So let's get started. The first integral, e to the x. Now, I guess I should point out, I have basically three strategies for evaluating integrals, finding antiderivatives. In Calc 2, you'll learn some additional strategies, but the three that we have for now are simply to recognize the integrand as the antiderivative of something, or sorry, as the derivative of something, which is just a wordy way to say just know what the answer is. But what I mean is when you see the integral of cosine of x, I see cosine of x and I just think, okay, what do I know whose derivative is cosine of x? Well, that would be sine of x. The derivative of sine of x is cosine of x, so the integral of cosine x is sine of x plus c. Or you might see the integral of 1 over the square root of 1 minus x squared. And that, it's got a square root, there's an x squared, stuff is in the denominator. It looks like it might be complicated to figure out, but there's really nothing to compute. You look at that and you say, I've seen this before as the derivative of something. Oh yeah, it's the derivative of arc sine of x. If you don't just remember what the derivative of arc sine of x is, you're never going to look at 1 over the square root of 1 minus x squared. And you couldn't just come up with arc sine of x. Now, of course, you could with enough time, right? At some point, someone had to figure that out. But in the stress and time constraints of an exam, it's hard to just come up with that if you don't just recognize that as the derivative of arc sine. So that's the first way that we do antiderivatives. The second method, which you'll see in a few of these dominoes, you need to simplify the integrand. And the third method is U substitution. So this first integral, I see e to the x, I think, what's a function whose derivative is e to the x? Well, that would be e to the x. Okay. I will try to find that domino, and then we'll go from there. E to the x plus c. Okay, so this one came from domino A, and now we're going to integrate 1 over e squared e dx. This looks a little bit strange. The thing that we're integrating doesn't even have any x's in it. That's just a constant. And if I say those words out loud, we are trying to integrate a constant. Now, you probably have an idea of what the integral is. The integral of a constant is just going to be that constant times x. Oop, I switched the e and the x. If I simplify this, I'm going to cancel out a pair of e's, and we'll be left with x over e plus c. There we go. This came from domino x. The integral of pi to the 2x. Okay, if this were just pi to the x, I would recognize this as the derivative of an exponential function, the derivative of pi to the x up to a constant factor. Because of that 2x, I'm going to try substituting u equals 2x. This is not necessary, but I think it's probably the easiest way to go about this. So if u is 2x, du dx is 2, which means du is 2 dx. Now there are two different ways that you can complete the substitution. One way to go about this, and they're not very different, but one way to go about this is to divide the 2 over, so that you see that dx is equal to 1/2 du. So I substitute the 1/2 du for the dx. What I like to do is, I know that du is equal to 2 dx. I wish I had a 2 here. I don't. But if I want a 2, I can just write in a 2, as long as I also add a 1/2. If I'm missing a constant factor, it's no big deal. I can add it in, and I can also, by add in, I mean multiply it in, and also multiply by the reciprocal. So now this is the 1/2 times the integral of pi to the u du. I just replaced that 2x with u, and I replaced the 2 dx with du. Okay, we still have to integrate this exponential function. Now you might think, if you have memorized the derivatives of the exponential functions, or if you sort of memorized an antiderivative rule for an exponential function, you might just know what this is. You might remember that there's an ln of pi. When we have an exponential function whose base is not e, we end up with an ln of the base. But do you multiply or divide by the ln of pi? If you don't remember exactly what you're supposed to do, I want to kind of show you how you would think through that. So if you don't remember exactly how to handle this, how do you work it out? Well, you should be inspired by the fact that the derivative of e to the x is e to the x, and think maybe I should try as my antiderivative pi to the x, or I guess 1/2 pi to the x. So we make a guess, and then let's check if this guess is right. It won't be, but actually going through the steps of checking this will show us what we need to do to get the right answer. A wrong guess is often productive in leading you to a better guess. So how do I check? If I think this is the antiderivative, I should take the derivative and see if I get the thing that I was trying to integrate. If I differentiate this, I get 1/2 times pi to the x. And we do need to at least remember the derivative of an exponential function. When you differentiate an exponential function with a base other than e, you end up multiplying by the ln of the base. So is that the thing that we were supposed to get? No, partly because I wrote x here when we have an integral in terms of u, so I should be working with u's. And we'll convert back to x at the end of the problem, of course. Okay, so I was supposed to just get 1/2 pi to the u. I got that, but I also got a factor of ln of pi. I don't want that there, so how do I deal with that? I'm going to divide by the ln of pi. And that's going to cancel out this unwanted ln of pi, leaving me with just the 1/2 pi to the u, which I wanted. So my antiderivative is 1/2 pi to the u divided by the ln of pi. Now, maybe you feel that I'm overcomplicating this. It is probably just the simplest to recall that the derivative, or the antiderivative of pi to the u is pi to the u divided by the ln of pi. When you differentiate an exponential function, you end up multiplying by ln of the base. When you anti-differentiate an exponential function, you end up dividing by the ln of the base. But if you forgot whether you were supposed to multiply or divide when you look for an antiderivative, I just wanted to show how you would think through that. So if I clean this up, I have pi to the u, which I'm going to rewrite as pi to the 2x. And then in the denominator, I have 2 times the natural log of pi. Let's see if that's one of the dominoes. It is. It's the one right above this. So this comes from domino R. Okay, next up, we are integrating the cube root of x to the 4th plus the cube root of x squared. Pet peeve of mine. I think that there should be parentheses there. Some people, I guess, interpret this to mean that the integral and the dx implicitly put parentheses there. Do we need to know broad generalizations of the trace of the square matrix for the final? P. Diddy lover. I don't know who you are or how you know about about the research that I did in grad school, but you certainly do not need to know about that. Heck, you don't even need to know about the trace of a square matrix for the final, let alone any generalizations. So how do I integrate this? I'm debating whether this is an example of number 2, simplify the integrand. We'll call it that. I'm not maybe even going to simplify it. I'm just going to rewrite this in a different way that's easiest to deal with. And what I'm vaguely hinting at is I'm going to rewrite these roots with exponents. So a cube root is the same thing as a 1/3 exponent. And when I have something to a power, I can combine those exponents by multiplying them. So this is just x to the 4/3 plus x to the 2/3. And we can integrate this by reversing the power rule. Now, in practice, it might be just the simplest if you commit to memory the fact that the integral of x to the n is x to the n plus 1 divided by n plus 1 plus c. But if you don't remember that exactly, how would you think through this? You would think, well, how do I get an x to the 4/3? I know that the power rule drops the exponent by 1 when I differentiate, so when I'm looking for an antiderivative, I should add 1. But then if I were to differentiate x to the 7/3, this is my guess and check strategy again, I would get 7/3 x to the 7/3 minus 1. But that's not what I want. I don't have a 7/3. How do I get rid of that unwanted 7/3? By multiplying by the reciprocal, 3/7. So my antiderivative of x to the 4/3 is 3/7 x to the 7/3. And of course, that's exactly what this rule is telling you to do. You divide by the new power that you get after adding 1, which was 7/3. And dividing by 7/3 is, again, multiplying by the reciprocal 3/7. Similarly, the x to the 2/3, to get that by differentiating, I would have to start with something x to the 5/3. And the coefficient that I need is a 3/5. And let me not forget the plus c. So 3/7 x to the... Oh. Wow, the Dominoes is just going up through this column. I wonder... Well, I guess the pattern has to break pretty soon. So this one came from domino L. And now we are integrating minus cosine of x times tangent of x. Okay, so this maybe is on the surface, it appears to be the most complicated integral we've seen yet, but let's just look at our methods. Do I recognize this as the derivative of something? Nope. Method 2. Could I simplify this? To see if this simplifies at all, it's easiest to rewrite any and all trig functions in terms of sine and cosine. And once I do that, this becomes very easy because all that I'm left with is minus sine of x. I think, what function would give me minus sine of x when I differentiate? Well, that's cosine of x. The derivative of cosine of x is minus sine of x. All right, so this one came from domino F. Oh, and this is exactly the integral I was talking about as an example of just recognizing this as recognizing the integrand as the derivative of something. This is arc sine of x. I should also point out, if you move on to Calc 2, you will learn another method to integrate this, although certainly the easiest way to integrate it is just to recognize what the answer is. But if you're curious, there's a method that you'll apply to more complicated integrals, but this is sort of the simplest one that it would apply to. You'll make a substitution. You'll say x equals sine of theta, or cosine of theta. So I will leave you all to think about how that would be a useful substitution to make. But for now, let's look for an arcsine of x. Here it is. This came from integral w. I'm really starting to suspect that the pattern actually does continue throughout all the dominoes. Wow. I have been doing this activity in my calculus classes for 5 semesters now, and I don't think I ever realized that if you lay the dominoes out alphabetically in rows like this, then they match together along the columns. That's very humorous. Okay, next we're going to integrate 1 over x. Again, this is another integral where the appropriate method is number 1, which is just to recognize that this is the derivative of ln of the absolute value of x. Plus c. All right, let's move on to the integral of sine squared of x times cosine of x. Okay, method 1. Do I recognize this as the derivative of something? Nope. Method 2. Could I simplify this? I can't see a way to simplify it. The last time we had a trig integral, there was a tangent, which I could rewrite as sine over cosine, but here I just have sines and cosines. The only thing I can think to do is to rewrite sine squared of x as 1 minus cosine squared of x, using the Pythagorean theorem, or the Pythagorean identity. But then I end up having to integrate cosine cubed of x, which I don't know a good way to do that. In fact, the way I know how to do that is to go in reverse and convert it back to something like this. Okay, all that to say, method 2 doesn't really work here. I don't see a good way to simplify this. So we're on to method 3, u substitution. Now, to make a u substitution work, you want to find somewhere in your integrand both an expression and then somewhere else the derivative of that expression. So I'm looking for a thing and its derivative. It might help if I rewrite this as sine of x squared times cosine of x. That's just what sine squared means. Okay, I see sine and cosine. And cosine's the derivative of sine. So when I see a thing and its derivative, I'm going to try a substitution where I set u equal to the thing. And then when I differentiate, I get cosine of x and there you go. So this integral becomes, well, I'm going to replace the u with sine of x, so that's u squared, and then this cosine x is equal to du, so the integral is just u squared. The integral of u squared is 1/3 u cubed plus c, and the last thing we should do is replace the u with sine of x, and I'm going to revert to the original notation because that's how I expect to see the answer. To be clear, you would get full credit for this. But if it's a multiple choice, or if it's a domino activity, I just expect to see the answer written this way. 1/3 sine cubed x plus c. There we go. All right, x cubed minus x over x squared. Method 1, do I recognize that as the derivative of something? No. Method 2, could I simplify this? I think so. I have a fraction with 2 terms in the numerator. I can split this up into 2 fractions. X cubed over x cubed minus x over x cubed. I see a lot of confusion about how to cancel. Like, a very common mistake here would be to say that these x cubeds cancel and maybe leave you with 1, right? Like, they cancel and leave behind a 1, and then you still have the minus x. So you get 1 minus x. But the cancellation doesn't quite work that way. And it might help to understand why you can split a fraction up like this. And it's really just, whoa! I just noticed they forgot the dx. That's crazy. Justin Barhick, biggest fan. Oh, thank you. Do we have to use U for the substitution, or can we use any letter? You can use any letter you want. I would maybe recommend not using D, because it gets confusing when you have to write things like DDDX. We're overloading the letter D there, but other than that, any letter is good. So why does the canceling work, or the breaking the fraction apart work this way? Well, dividing by x cubed is the same thing as multiplying by 1 over x cubed. And while I see a lot of students who aren't quite sure how to cancel or to split up this fraction, I think most people are pretty comfortable with the idea that when you multiply something with a sum or a difference of 2 terms, you have to distribute that multiple to both terms. So this becomes 1 over x cubed times x cubed minus 1 over x cubed times x, which is the same thing that I've written down here. Now if I simplify this, x cubed over x cubed is 1, x over x squared, I could simplify that to 1. I'm not sure what I said. X over x cubed, I could write that as 1 over x squared. But for the purposes of anti-differentiating, as we saw in this example, it's often helpful if you can write something as a power of x. So instead of 1 over x squared, I'm going to use a negative exponent and write that as x to the minus 2. Can't believe they left out the dx. Yeah, and again, I've been teaching with this activity for 5 semesters now, and I can't believe I haven't noticed that until this point. So the antiderivative of 1 is x. The antiderivative of x to the minus 2 is, and I'm using the reverse power rule once again, I bump the power up by 1 and divide by that new power. So I go from a negative 2 up to a minus 1, and I divide by a minus 1. So I get x plus x to the minus 1, which is 1 over x. Yep. And again, it does not matter whether you write x to the minus 1 in your answer or whether you write 1 over x, just as long as you can recognize that those are the same in case the multiple choice answer is not in the same, it's not the same one that you wrote down. Okay, minus 1 over x cubed. This dx over x cubed can be a little confusing, but all this means is we're integrating 1 over x cubed with respect to x. Normally when you multiply two quantities like this, right, you could bring the dx up there. That's all that's going on. Just like in the last problem, I'm going to rewrite the 1 over x cubed using a negative exponent. And then, whoops, I almost wrote x to the minus 4, but no, minus 3 plus 2, minus 3 plus 1 is minus 2. And then I divide by a minus 2. So it comes out to 1/2 x to the minus 2 plus c, or if you prefer to write that with a positive exponent in the denominator, that's 1 over 2x squared plus c. Anyone Fouriering their transform right now? I don't think I want to say. Will we get arrested if we forget to write the plus c? Quite possibly, yeah. You would almost certainly lose 1 and only 1 point. They will beat you. No, I have better things to do than track down people who omit the plus c and beat them up. And I want to keep my job also. But we will take off a point. So that, yeah, how do you know when to put a plus c? When you're doing an indefinite integral, which means there are no bounds, you have a plus c. When you have a definite integral, meaning that there are bounds, there's not a plus c. I think it helps to remember that if you understand the reason why. Jack Dalton's biggest fan. Jack Dalton is also my favorite occupant of Math 223. That's a good call. What was I saying? Oh, yeah, so why do you have the plus c? Because an indefinite integral means what is the most general antiderivative, which really means what are all of the antiderivatives. And if you add on any constant, you get another antiderivative. So to say what all the antiderivatives are, I write the plus c to indicate that any number there would result in an antiderivative. When you have a definite integral, this is representing the area between 1 and 4. That area is just one fixed number. There's just one number that is the answer. If you write a plus c on a definite integral, you're saying that this area could be literally any number, but that's not true. It is one particular number. Okay, so put the plus c. Which one were we on? ln of x over x. Okay, method 1. Nope, I don't just know what this is a derivative of. Method 2, could I simplify that? No. If you cancel those x's, you will definitely go to jail. That is not okay to cancel these x's. Right. The x here on the top is being plugged into the natural log function. So that leaves us with method 3, making a u substitution. This canceling the x's there reminds me of a classic math joke. Sine of x divided by n. Cancel the n's. You get 6. And yeah, canceling these x's would be almost as bad as canceling those n's. Can we cancel the ln? What would you cancel it with? There's nothing to cancel it with. Okay, so that leaves method number 3. You, Seb. Do I see a function and its derivative? I see an ln of x. What's the derivative of ln of x? It's 1 over x. Yeah, 1 over x. An x in the denominator. U equals ln of x is going to be the substitution that gets the job done. So the ln of x gets replaced with u, and the dx over x gets replaced with du. The antiderivative of u is 1/2 u squared, and we end up with 1/2 ln of x squared plus c. Cosecant squared of x. All right, number 1, do I recognize that as the derivative of something? Almost. If I think about my trig functions, and honestly, you have 2.5 hours, it would not be the worst thing in the world to, once the exam begins, just turn to a blank page at the end. There's no blank page at the end. I just printed them all. But there is a blank page on the back of the bubble sheet for the multiple choice. Once the exam begins, and not a moment before we say you can start, but once the exam begins, flip that multiple choice sheet over and just write out all of the derivatives of all the functions you know. Because somewhere in the list of your derivatives of the 6 trig functions, you'll see that the derivative of cotangent x is minus cosecant squared of x. And then when you try to integrate the cosecant squared of x, you'll recognize that's the derivative of cotangent of x if I only had a minus sign. But it's fine. I can just throw in 2 minus signs. To see that the antiderivative of cosecant of x squared is minus cotangent of x plus c. Your mathematician is cooler than me. Well, Jack Dalton's biggest fan. I just have to ask, why is Jack Dalton not talking to 19 people on Twitch right now? That's all I have to say about that. Just my biggest fan. Thank you for for defending me there. Ban him? Oh, I couldn't. Also, I bet your mathematician is a Packers fan. Lions, good catch. I don't know if Jack is a Lions fan. But that would definitely make him significantly less cool than me. A very funny thing about the chat being so lively right now is that Twitch is identifying 2 of you as possible ban evaders, which is very interesting. I don't know why it thinks that. All right. Moving on to the integral of cosine of x dx. And this weird line. How did this get... Did I do that? I don't know. Okay. Well, this is a classic method number 1 integral. What is cosine of x the derivative of? Sine of x. Nothing more to say about that. Plus c. I'm not saying the plus c out loud every time, but I am writing it every time. Okay, integral of 1 over x squared plus 1 dx. Do I recognize that as the derivative of something? Yes. That's the derivative of arctangent of x. And again, if you don't just recognize that, you're going to have a hard time figuring that out on the fly during the exam. Will we get glorious math Twitch streams in Calc 2, or are we just left to rot? I've been toying around the idea of doing some streams next semester for Calc 2. I'm not teaching Calc 2, but Calc 2 is, there's a lot of really interesting stuff there. I didn't like Calc 2 until I taught it, and I had a better sense of why things were important. So I've been thinking about maybe doing some streams and showing you some cool applications, maybe trying to help make sense of why do you want to think about infinite series or Taylor series, applications of integration. But this is why Dr. Barhydt is the GOAT. All right. Arctangent of x plus c. Yep. Integral of secant of x tangent of x. This is method number 1. Since I hypothetically, after the exam began, wrote out on the back of my multiple choice sheet the derivatives of all the functions that I know about, including all 6 trig functions, I would have written down that the derivative of secant of x is secant of x times tangent of x plus c. Oh, just 1 PhD. That is enough for anyone. Mr. Dr. Barhydt is also acceptable. Secant of x plus c. Yep. Now, if anyone asks you to integrate secant of x plus secant of x with respect to x, that's a good time. But it's a good time that we're not going to have now. You might have to wait until Calc 2 for that. 1 over cosine squared of x. Is that something I recognize the derivative of? Not immediately, but this is actually a combo of methods 1 and 2. So after I fail to recognize this as the derivative of something, I'm going to move on to method number 2. Can I simplify this? I do actually know a way to rewrite this. 1 over cosine of x is, we have a name for that. That is secant of x. So 1 over cosine of x is the integral of secant squared of x. And notice I still wrote the integral sign because I have not anti-differentiated yet. I'm only rewriting the integrand. I'm noticing something interesting, which is that in, I think, one of the very first ones we did, we simplified by rewriting the tangent in terms of sine and cosine, whereas here I had only sines or cosines, just cosine in particular, but I found it helpful to rewrite this in terms of secant. So it's not even always a question of simplifying. It's just, there might be various ways that you could rewrite the integrands in a way that's more amenable to integration. There's a Mr. Dr. Barhydt in the chat. I don't know who that is, but that's not me. That is an imposter. Mitosis is the Mr. Dr. Barhydt another copy of me that's been formed by mitosis? Or are you also just studying for a biology final? Calc is short for calculator. That's a fun fake fact. The truth is way cooler than that even. The word calculus comes from a Latin word that I believe means pebble. Will we need to integrate the square root of the tangent of x? Square root of the tangent of x. I don't know off the top of my head how to do that. So I'm guessing no. You would not be expected to integrate that. And I want to kind of play around with that, but maybe I'll do that on my own time. So secant squared of x. Now we're back to method 1. I recognize that as the derivative of tangent of x. All right, integral of sine x minus cosine of x plus c. Method 1. E to the 2x. USEB. Maybe I'll stop explicitly going through my 3 methods every single time, but I hope you get the idea. I am sort of going through this mental checklist on every single integral I see. Or I would be if I weren't teaching calculus for the 5th semester in a row. So by this point, I just look at the integral and I know what to do. But yeah, if you're not sure how to do an integral, just think through those 3 different possible approaches. Once again, I wish I had a 2, so I'll add 1 in, and I'll also multiply by 1/2 to cancel it back out. But I end up with e to the u du, and an integral sign. Integral of e to the u is e to the u. There we go. 1/2 e to the 2x plus c. X to the n. We already wrote this down. That's x to the n plus 1 over x to the over n plus 1 plus c. Supplemental Sunday review. Before the gangster computer god controlled phony math professor puppets. Oh my goodness. If there are multiple people interested, and if you all can agree on a time, I am open to this. Oh, I see. I've been getting some new followers. Thank you, Azul, Bapanada Inc., No 7 Mac, Witty Bloom, Jawless Love, Breadman the Man. Thank you all for following me. I'm encouraged to maybe hop online tomorrow by the fact that the chat has been so lively. It's a lot of fun when we've got 20 people here and people are engaging. Some of the review sessions have been a little quieter, which is fine too, as long as people are watching them and getting some value out of it. But if I wanted to integrate the 5th root of x, we've seen similar things. I'm just going to rewrite that with a fractional exponent. The 1/5 is going to get bumped up to a 6/5, and I will divide by 6/5, which is the same as multiplying by 5/6. All-time record for viewership? Yeah, 20 viewers. For me, that might be an all-time high. Champ Davis Goat, thank you for following. Are you all students here at CU, or are you some of you from Wayne State? And did my friend Shazad tell you to tune in? Okay, overwhelmingly CU. Okay. This is definitely not method 1. I don't look at that and just know what the answer is. But method 2 is going to help here. If I distribute the 6x cubed, Mathzetti, haven't told any of your students. Well, feel free to. I mean, there's maybe one more session tomorrow, but if you think they'd find it helpful. I'm glad you're here, though. So I've distributed that 6x cubed, and now this is just a polynomial. So the x to the 4th goes up to x to the 5th, and I divide by 5. The x cubed goes up to an x to the 4th, and I divide by 4. 12 divided by 4 is 3. There we go. Oh, that's very respectful. But of course, you are more than welcome to help me build a base of loyal followers. Although I suppose I might want to dial back the criticism of the Detroit Lions if there are going to be any people from Wayne State in here. X to the... What did I do wrong? Oh, geez. 3 plus 2 is not 4. Whoops. There we go. X to the 5th. So 6x to the 5th, which becomes x to the 6th. This is a fun one. Method 1, I don't quite recognize this, but I see that square root in the denominator with an x squared being subtracted, and it's definitely setting off arc sign alarm bells in my head. But it's not quite an arc sign. So if I move on to method 2 and think about how I could simplify this, we'll get that arc sign. Don't you all worry. We'll make this an arc sign. If I pull out that 4 inside the square root, square roots break up across... oh my goodness, plus c. The only thing worse than forgetting a plus c is writing a plus c where it doesn't belong. That should be a dx. Okay, so the square root breaks up across multiplication, and I just want to remind you all, because this is a very common mistake, square root does not break up across addition or subtraction, only multiplication or division. So the square root of 4 is 2. I end up with 2 over root 1 minus x squared. We can even pull that 2 outside of the integral because it's a constant. And we're going to end up with 2 arc sine of x plus c. Two arc sine of x plus c. Okay. X to the pi over x. Method 1, no. Method 2, I do know how to simplify this. Someone asked me about this at the end of class yesterday, and right, you might have the feeling that this should simplify somehow, but if you don't remember exactly how to simplify this, I find it's helpful to replace the pi with a number. A different number, to be clear. Pi is not 3. But it's easier to see what you do when you have numbers instead of symbols. What would you do here? Well, that's x squared. You cancel the x in the bottom with one of the 3 x's in the top, but this might remind you that the exponent rule says when you divide powers of x, you subtract the exponents. So x to the pi divided by x is x to the pi minus 1, and that antiderivative is going to be x to the pi divided by pi plus c. Pi equals e equals 3, yeah. Yep. Sometimes mathematicians like to make fun of engineers, but we shouldn't be making fun of engineers. We should be making fun of astrophysicists because they just round everything to the nearest power of 10, right? Order of magnitude. What's the difference? Pi is 1, pi is 10. It's all good. A to the x. We've already talked about integrating exponentials in a lot of detail. More detail than you probably wanted to see right over here when we integrated pi to the 2x. But this is just going to give you a to the x divided by the ln of a. Well, that's it. We've gone through the entire integral Dominoes activity. Questions about anything specifically related to finding antiderivatives before I move on to the practice exam? Dr. Prof. Okay. Oh, this is interesting. So Mr. Dr. Barheit, Twitch also thinks you are a possible banovator. I think the pattern is anyone with... Seems like anyone with either my name or Jack Dalton's name in your username. It thinks you might be a banovator. I'm very curious why that is. New accounts, yeah, but... There are other new accounts too, I think, that aren't getting flagged like this. I don't know. But Mr. Dr. Barhead, thank you for following. And Roses of May, and Chips and Dips, and Champ Davis Goat, thank you for following. All right, once again, send me questions in the chat or in my email. Otherwise, I'm going to move on to the final exam from last semester. Fun fact, last semester is the first time, at least in recent history, that we've done these short answer questions in addition to multiple choice and free response. That's one of the reasons why we put up this new set of exams from last spring, so you would have some practice exams with with the same format as the real one. When will I be getting Twitch partners so we can buy subs? First of all, even if you could subscribe to me, no one should pay me money for this because I am teaching Calculus 1. It would be highly unethical for me to accept payment from anyone for services related to a course which I am teaching. But I think now that we're over 25 followers, that was the big one, big requirement to get a Twitch affiliate status. This stream might put me over. Can we do a Calc 3 review after I'm done with Calc 1? Roses of May, are you in both Calc 1 and Calc 3? Because I know I know of exactly one student in that situation. Just hanging out. Okay. I might be willing to answer a few Calc 3 questions once we get through the Calc 3 stuff. If I remember how to do them. I haven't thought about Calc 3 in a while. Fun fact, I never took Calc 3. I learned most of Calc 3 from physics classes, but I never took it. Okay. Let's do this exam. Penny is dropped from a height of 20 meters from the ground. If it takes 2 seconds to hit the ground, what is its average speed as it falls? Okay. So it goes 20 meters in 2 seconds. 20 meters. Well, let me switch the thickness of the pen. 20 meters divided by 2 seconds is 10 meters per second. This is average rate of change. The general formula for average rate of change is f of b minus f of a over b minus a. So why do I not have 4 things? Why do I only have 2? Well, I was, if you wanted to, if you want to write it out with this formula, you would say it starts at a position that you're calling 0 at time 0, and then 2 seconds later it's at position 20. Okay. We're evaluating the limit. Ooh. I'm going to do this the way that you should do it. I'm also going to do it the fun way. I'm going to do the fun way first, because it'll be more satisfying to check it directly. I recognize this as the derivative of a function evaluated at 1, where f of x is x squared. Is that right? The derivative, and I'm not only doing this for fun. I also think it's good to review the limit definition of the derivative. F prime of 1 would be the limit as h goes to 0 of f of 1 plus h minus f of 1 over h, which is the limit as h goes to 0 of 1 plus h squared minus 1 squared over h. Yeah, okay. So this is the derivative of the quadratic function x squared evaluated at 1, but using the power rule, I know that that derivative is 2x, and so f prime of 1 is 2. This will be on YouTube, yeah. Just as soon as Twitch can export it after the stream. Yep. Okay, so how would I recommend actually doing this limit on the exam? Let's just, well, okay. The first thing that you always try in a limit, I almost skipped right past this. The first thing you always try is direct substitution. So if I plug in 0, I get 0 over 0. Now, a common mistake would be to get 0 over 0 and conclude that the limit does not exist. That's not true. Getting 0 over 0 could mean anything. Maybe the limit doesn't exist. Maybe the limit does exist. You have to do more work to figure out whether it exists. And the work in this case is just going to be expanding that h plus 1 squared and doing some algebra to simplify. The 1's cancel. So I have h plus 2h over h. Now we have to cancel, and again, cancellation can be dangerous. A common mistake is to cancel those h's, leaving yourself with 2h. Oh, sorry. That was h squared, not h. But still, a common mistake would be to try to cancel somehow with just the first term. What I recommend to avoid any cancellation issues is factor an h out of the numerator. These h's do cancel, so you're left with oh, sorry. Oh, I'm making a lot of mistakes on this problem. When I factor out an h, I'm left with h plus 2. Now I can do direct substitution, and I get 2, as expected. Evaluate the derivative of arctangent of x over 2 when x equals 2. Okay, so the derivative of arctangent of x is 1 over 1 plus x squared. But the derivative of arctangent of anything that's not just an x it's not quite as simple as just 1 over 1 plus that thing squared. The chain rule says you also have to multiply by the derivative of whatever that thing was. So if I have x over 2, I'm going to get 1 over 1 plus x over 2 squared times 1/2. And they wanted me to evaluate this at x equals 2. So I'm going to get 1 over 1 plus 2 over 2 squared times 1/2, which is 1 over 2 times 1 over 2, or 1/4. K. McCollum, why would you not plug 2 in first, get arctangent of 1, and use the chain rule? That's a really good question. That approach would be wrong. You're going to get 0. But I'm really glad you brought this up, because this is a very common mistake in related rates problems. So let me just show you what happens if you plug in the 2 first. So if I'm trying to differentiate arctangent of x over 2, and I plug in arctangent if I plug the 2 in for that value of x, so the arctangent of 1 is pi over 4, which is 45 degrees. Pi over 4 is a constant. Arctangent of 1 is a constant. Of course this is a constant. There are no x's in it. And the derivative of a constant is 0. Now you also suggested using the chain rule here. I just want to point out that the chain rule doesn't save you. You still get 0. Because maybe I do 1 over 1 plus 1 squared. So I'm sort of using this idea. It's going to be 1 over 1 plus whatever that thing was squared times the derivative of 1. But that's 0. So you're going to get 0 no matter how you do this. The point is that if you substitute in a specific value of x, then you just get a constant, and the derivative is 0. This happens often in related rates problems. You're given, you write down an equation modeling the situation. You're also given some information about a specific moment in time. Like, how fast is the water level rising when the height of the water is 5 meters? The problem is if you plug in that 5 meters to the volume equation before you differentiate, this exact thing is going to happen, where you're going to get something nonsensical, like 0. The way I describe this with related rates problems is that to understand the rate, we're thinking about how something changes over time. we need to see it evolve over time. It's like you want to write down an equation that is true for all moments in time. I think of this as like taking a video of whatever is going on, the water level in the tank rising. In order to see how fast the water level is rising, you need to look at this video so you can see it changing. When you plug in that value, like the height being 5 meters, plugging in that value has the effect of, taking that whole video, but just deleting everything except one snapshot at the single moment of time when the height is 5 meters. If you don't have the video, if you just have that photo, you can't see how fast it's changing. You can't even tell whether or not it is changing because you just have that one still frame. It's the same sort of thing going on here. I'm asking how arctangent is changing at a particular moment in time. But if I plug in a specific value, it's kind of like I'm taking the graph of arctangent of x over 2, and the rate of change is the slope of the tangent line. But if I plug in 2 like this, what I'm doing is I'm just like, I'm covering up everything in the graph except that one vertical slice at x equals 2. So all I see is a single point. And I can't tell what the slope of the tangent line is if I only see that one point. That was a very long-winded answer. But I wanted to go into a little detail there because this is a very common mistake on related rates problems. The TLDR is, if you're asked about a rate of change at a specific moment in time, you have to differentiate before you plug in anything that is specific to that one moment in time, or specific to that one x value. All right, keep the questions coming, but I'm going to move on to number 4. We're going to differentiate. Oh, okay, yeah. This is a classic kind of problem. We give you a graph, we give you an equation. We ask you to show us that you know how to do the chain rule and the product rule. So the derivative of a product of f and g is f prime of x times g of x plus f of x times g prime of x. And they wanted to know this at x equals 1, so it's f prime of 1 times g of 1 plus f of 1 times g prime of 1. F prime of 1, ooh, wow. They give me a piecewise equation here. Okay, so I'm trying to plug 1 into the derivative. Let's go ahead and just compute the derivative. When x is less than 1.5, the derivative is going to be 1/3 x to the minus 2/3, and when x is greater than 1.5, the derivative is going to be pi times cosine of pi x. The chain rule is why I get this extra factor of pi. So f prime of 1 is less than 1.5, so I will plug that in here. That's 1/3 times 1 to the minus 2/3. And then g of 1, I'm just going to look at the x value of 1 and read off the y value. That is 2. F of 1, once again, 1 is still less than 1.5. So I'm going to plug that into this first row. And I'll get 1 to the 1/3 plus 1. And then I need g prime of 1. G prime of 1 is the slope of the tangent line right here. That's a straight line. So what's going on? If I go over 1, it's also going up 1. So that's a slope of 1. 1 to the minus 2/3 is still just 1. Because you're squaring it, taking the cube root, and taking the reciprocal because of the negative sign. But every single one of those operations leaves 1 unchanged. And then over here I have 2 times 1. So this is 2/3 plus 2, which is 2/3 plus 6/3, or 8/3. Whew! That was a lot of work for a single multiple choice question. All right. This next question is going to require the chain rule. The derivative of f of g of x is f prime of g of x times g prime of x. When I evaluate this at x equals 3, I get f prime of g of 3 times g prime of 3. G of 3 is 2. Oh, you all saw that low battery warning. That's concerning, to say the least. Oh, we've been going for an hour and a half. That's why my battery is low. All right, can I finish this exam before the battery dies? All right, well, I'm going to go fast. All right. G prime of 3 is the slope of the tangent line at 3. Once again, no, the slope is not -1. If I go over 1, that's the same, that means I go down 2 units. So that's a slope of -2. Do I not have a charger? Great question. I do have a charger, but there's only one port. And right now my iPad is plugged into a cable in order to stream. I did do a stream before I had the cable. What I did then was I set up a Zoom meeting and I shared my screen. I could try that if we need to keep going after the battery dies. All right, f prime of 2. 2 is bigger than 1.5, so I'm going to plug 2 into that second formula, and we'll get pi times cosine of 2 pi times -2. Cosine of 2 pi is 1, so we get -2 pi. It's not just Apple, though. I mean, my Android phone, they used to have the charging port and a headphone jack. Now they just use the same one. That's annoying. All right, limit. X is going to -infinity. Okay, so this piece, 1 over a really large negative number, plus 1, is going to be basically 0. It's going to be a very small negative number. So it's going towards 0. Now, x squared, this thing is approaching positive infinity, because a large negative number squared is a large positive number. So the thing I'm plugging into the ln function is getting larger and larger. The ln function, if I just sketch a quick graph, you can see as the input to the ln function gets bigger, the output is also getting bigger. So the ln of x squared is going to infinity. If you add things that are approaching 0 and approaching infinity, the result approaches infinity. Okay, limit as x approaches -2 from the right of 10x over x plus 2. Okay. So this 10x is approaching That's approaching negative 20. Right? If I just plugged in negative 2 to the numerator, I'd get negative 20. The bottom, that x plus 2, I'm plugging in things that are just a little bit bigger than negative 2. When I add 2 to that, I'm going to get something that's just a little bit bigger than 0. So I'm dividing things that are basically negative 20, I'm dividing them by things that are slightly bigger than 0. The result is going to be something, well, it's negative because I'm dividing a negative number by a positive number, but it's also getting bigger and bigger because the numerator is staying around negative 20 and the denominator is going towards 0. So this is going to be negative infinity. A more concrete way to think about this would just be to imagine plugging in like a very small number, a number that's very close to negative 2, but greater than negative 2. So plug in negative 1.99 and see what you get. You should get a fairly big negative number, which is not proof that the answer is negative infinity, but it's suggestive. Okay. When x approaches infinity or negative infinity and you have a rational function, you could actually do L'Hopital's rule. But I think the most straightforward way is that when you have a rational function, again, and x is approaching infinity or negative infinity, it all comes down to the leading terms in the numerator and the denominator. So I can ignore everything, I can ignore the 2, which is everything in the numerator except the x squared. And in the denominator, I can also ignore everything except the x cubed. And to be clear, these expressions are not algebraically equal. It's just that when we take the limit as x goes to infinity, you're going to get the same result in the limit. Would you look at that? The x to the 6th cancel, and you're left with 1/2. What's going on is that we have the same exponent in the numerator and denominator, and when that happens, the limit gives you the ratio of the leading coefficients. What is the slope of the tangent line to the graph of xy equals sine of x at the point pi 0? Okay, slope of the tangent line, that means derivative, so I'm going to differentiate both sides of this equation. I'm going to use the product rule here, so I'll differentiate the 1, and then in the second term I'll differentiate the y. That just gives me dy dx. And if they asked us for a formula for dy dx, we would solve this by bringing the y over to the right side and dividing by x. But since they gave us a specific point, I don't actually even need to do that. Star Girl, I see your question. I'll come back to that in just a second. We don't even need to solve for dy dx algebraically. What I mean is we can plug in the values first. If I plug in 0 for y and pi for x, we just get pi times dy dx equals cosine of pi, which is minus 1. So dy dx is minus 1 over pi. All right, does leading coefficients always mean highest exponent or just the first one? That's a great question. It means the highest exponent, not the first one. Like if I wrote the denominator here as 1 plus 3x plus 2x to the sixth, the leading exponent, or the leading coefficient, is still 2. It's not 1. It's the largest exponent, not just the first one. Occasionally on these exams, you might see the terms in non-decreasing order, in increasing order instead, just to test whether you know exactly that thing, whether you know that it's the highest power, not just the first term. All right. We've got some sign charts for position, velocity, and acceleration, and they want to know when the particle is speeding up. A particle is speeding up when its acceleration and its velocity are in the same direction. It's being pushed in the same direction that it's already going. So that'll happen when the velocity and acceleration are both positive, or when the velocity and acceleration are both negative. So it looks like it's going to be 0 to 0.5 and 1 to 1.5. Oh, this is nice. It's a linearization problem, but you don't even have to compute the linearization. It was given to you. You just have to figure out what to plug in. So the point is that, well, what number do I need to plug in to the function to get the square root of 5? A common wrong answer here would be plugging 5 into the linearization. But let's look at what happens when you plug in 5 to the function. You get the square root of 5 plus 4, which is the square root of 9, which is 3. That tells you about the square root of 9. We wanted to know about the square root of 5. What do you have to add to 4 to get 5? You have to add 1. So 1 is the thing that you have to plug into the function to get the square root of 5. And that means that to get the approximation, I'm going to plug 1 into the linearization. That'll give me 9/4, whereas a decimal, 2.25. If I just quick Google what the square root of 5 is, because I'm curious, it's about 2.24. Alright, a function f is continuous on the interval 2 to 4, differentiable in 2 to 4 with f of 2 is 5. What additional condition will be sufficient to guarantee that there is a point c in 2 to 4 is a prime of c is 0? Okay, so this is a mean value theorem question. The mean value theorem tells me that there is a value c, under these conditions, there is a value c such that f prime of c is equal to f of b minus f of a over b minus a. This is saying that the instantaneous rate of change equals the average rate of change, but only at some value of c. The point is that the average rate of change is the slope. It's the slope of this secant line. And the mean value theorem says that there does have to be at least one point where the tangent line has exactly that same slope. Now, in this situation, we're wanting to be able to conclude that f prime of c equals 0. In our case, the a is 2, the b is 4. So f of b would be f of 4. F of a, that would mean f of 2. And then 4 minus 2. So 0 is equal to f of 4 minus 5. That's what f of 2 is. Over 4 minus 2. 4 minus 2 is 2. So that says that f of 4 minus 5 equals 0, which says that f of 4 has to equal 5. Let me pause here for questions, and I might have to the other tricky thing is I don't have a charging cable long enough to reach I don't have a cable long enough to reach my iPad. Someone's knocking on my door. That's very strange. I'm going to go see who that is. I'll be right back.
We don't have a charging cable, but we brought you snacks.
Oh my goodness! Thank you so much.
We definitely stream snack you.
You know what? I'll take one of these, but I'll leave these.
Oh, thank you so much.
Thank you, thank you.
Thanks so much. Have a good night. Stream snipers. Yes, that was a couple of folks who I guess were watching the stream and were kind enough to bring me some Haribo and a Rice Krispie treat, which doesn't help with the iPad, but does help with my mood. So, what can I do? Let me think. Someone quick get me a cable. Yeah, the problem is the nearest outlet is a few feet away, so it'd have to be like a 6-foot cable, which I have one at home, but we have been going for an hour and 42 minutes. We could just why don't I do as much as I can before my iPad dies, and then I'll do another session tomorrow to finish up this exam, maybe go through parts of the other ones. It's lightning. Oh, which means I don't even have one that long at home, because the one that I have is a USB-C. Alright, limit. Try direct substitution first. That's always what you should do. ln of 1 is 0, so I get 0 over 0. Okay. Direct substitution doesn't work, but this is a 0 over 0 indeterminate form. That tells me that I can use L'Hopital's rule. So this is the limit as h approaches 1 of, and now a common mistake here would be to differentiate the entire expression as a fraction using the quotient rule. But actually, L'Hopital's rule doesn't want us to do that. It does just want us to differentiate the top and the bottom individually. So the derivative of ln of x is 1 over x. The derivative of x minus 1 is 1. 1 over x over 1 simplifies to 1 over x. And now direct substitution works just fine. So I get 1. okay. Limit as x approaches negative infinity of x e to the x. The x part is approaching negative infinity e to the x. If I think about what the graph of e to the x looks like, as x approaches negative infinity, e to the x is approaching 0. So this is a 0 times infinity, or I guess 0 times negative infinity, indeterminate form. The way that I handle that is by putting one of the terms in the denominator, but as its reciprocal. E to the x over 1 over x is the same thing as x times e to the x. Now, what if I put the e to the x in the denominator instead? X divided by e to the minus x is the same thing as x e to the x. So either of these, right, these are both equal to the original x e to the x. One of these looks much more appealing to me because I just have a feeling that since this one has an x and that one has a 1 over x, this one is going to get simpler. Whereas when I differentiate this, I'm going to get a minus 1 over x squared. So while this is equal to this, I don't think this is going to... We're not going to make progress if we try L'Hopital's rule there. And I guess the point is that this is an infinity over infinity indeterminate form. Whereas this one is a 0 over 0. The derivative of x is 1. The derivative of e to the minus x is minus e to the minus x. And I can directly substitute. So that the reciprocal of e to the minus 1 is just e. What? What did I do? That's not an answer. X is going to negative infinity. Why did I switch to writing x approaches 1? Oh my. Oh, my iPad is at 1%. It's about to die. But apparently my iPad is not the only thing that is depleting. I think I'm also getting a little tired here. But this is the limit as x approaches infinity of minus e to the x, which is, sorry, negative infinity. We're approaching negative infinity. That's 0. Because the graph of e to the minus e to the x looks like that. So as we approach negative infinity, we're still approaching 0. We can try another one, but I'm at 1%. There's not a lot of time left. Riemann sum using right endpoints. Wow. Why don't we actually break here? Because this is where we get into the final portion of the course that's beyond midterm 3. It's the new material. And I've done a lot of stuff from that portion of the course in the past few review sessions. So you have some videos on YouTube you could look over before tomorrow. But I know a couple of people said tomorrow afternoon. I don't remember if anyone said any specific time. Azul said afternoon works great. Mr. Dr. Barheit said, let me check my schedule. And then did you check your schedule? You didn't tell me anything about your availability tomorrow. 3 p.m. That seems as good a time as any. So, No 7 Max says 4. Anyone else have an opinion? Bapanada Inc. says 4. Jobless Love says 4 is good. So, let me check my calendar. Oh, you all want it to be late. Mr. Dr. Barheit says 4. You all want it to be later, but that gives you less time to study after the exam. I mean, I'm not telling you how to live your life. I'm just all right, I looked at my calendar and I have nothing. Oh, there goes the iPad. $7:45 a.m. Monday. Well, I'm going to be busy proctoring the exam, so that will not work, unfortunately. But I'll plan to be back at 4 p.m. tomorrow. If there's anything in particular you'd like me to talk about beyond just working through the rest of that practice exam, feel free to shoot me an email. Otherwise, thank you all so much for joining, and thanks for being a lively chat. It's a lot more fun when people are engaged and I'm not just talking to a computer.